Okay, so this is going to be another indeterminate example, except we're going to be working backwards this time to find P. So the last example we were given P, we worked forwards. This time we're working backwards. We have a solid aluminum rod. It's connected to a solid bronze rod at flange B. The aluminum rod has an outside diameter of 100 millimeters. The bronze has an outside diameter of 50 millimeters. I guess I have these backwards, 1 and 2. That's weird. They put 1 on the bottom and 2 on the top. The normal stress in the aluminum rod must be limited to 0.62 of yield stress. Determine the maximum downward load of P, and then the deflection of the flange at B of the load determined in part A. Okay, so I'm going to start with labeling everything. So down here I have my aluminum rod, and this is from A to B. Okay, and the aluminum rod has an outside diameter of 0.1 meters, so that means its area is pi over 4d squared. And again, I just like to write all this stuff out from the very beginning. I have an initial length of 0.5 meters. Everything I want to have is in meters and newtons. I have a modulus of elasticity of, we are looking at aluminum, so I have 73 times 10 to the mega giga ninth pascals, Newton meters. I have a yield strength of 290 times 10 to the 6th pascals. Again, I get rid of the mega, so it's times 10 to the 6th pascals. So everything is in newtons and meters or meters squared. Up here, I have, if this is aluminum, then this is the one that's solid brass. It's nice that it's solid. I don't have to worry about an inside diameter. This is going to be our B to C. And if we look through here, the outside diameter, so we have a diameter of B of 0.05 meters. So we have an area of pi over 4.05 squared. I have a length of 0.9 meters. I have an E, brass, of 115 times 10 to the 9th. I have a yield of 124 times 10 to the 6th. And I think that's all I need right now. Again, it's just easier for me if I kind of have a chart with everything in the same unit. So when I get my formula set up, it's just a matter of plugging things in. So we need to go back and find this P. Well, if I apply a load with this P, I'm going to end up with a reaction at A and a reaction at C. And I know that my internal is a function of that reaction. And I know if I'm pushing up, that internal is a function of the reaction. And stress is that internal over A, and delta, if we're in the elastic region, is P, that internal, length, A and E. So I'm going to set everything up just like we did last time. We're going to start with a free body diagram and equilibrium, because we always start with statics, always, always. And I have my system here, not drawn to scale, and it looks pretty scary at this point. But I have a load P, and I'm going to end up with a force from A to B. Actually, we're going to call that force at A because it's at my reaction. And I have a force at C. And so if I look at statics and I sum forces in the y direction equals 0, I know that FA plus FC has to equal P. And again, just like last time, I'm going to also look internal. So I cut it. If I have FA, then I know that FAB is equal and opposite, so FAB equals negative FA. And if I have FC, it's in tension, which we would assume it to be in tension, so FBC equals FC. Sorry, you guys can't see that, okay? So I have this set up with equilibrium. I'm going to assume both of these are pulling up. If this is pulling down, we have to be pulling and pushing. So internal, I would assume in tension. based on equilibrium, I would find it is in compression. So my internal FAB is negative FA. That negative tells us that it's going to be in compression. FBC equals FC. Positive tells us it's in tension. That makes sense with my picture. Pushing, pulling. Okay? So now, step 2, deformation. And we start with our geometry. So if I have my system, okay, and I load it, and I have A, B, C, and I'm loading at P, then again, I know that, what do I know? I know that the deformation of A to B and the deformation of B to C have to be equal. I know that delta AB, just like last time, plus delta BC equals 0. Okay? And what is delta? Force, length, area, modulus of elasticity. So I'm going to have the force in AB, length of AB, area of AB, E of AB, plus force of BC, force of BC, length of BC, area of BC, E of BC equals 0. Well, I have an equation over here that's set up with my external reactions in terms of FA and FC. And here I've got FAB and FBC. Okay, so that's where I have to go to this relationship of over here of what my internal forces are in terms of my reaction. So again, statics, equilibrium, internal forces, deformation, and geometry. And what is FAB equal? We have negative FA, length of AB, area of AB, E of AB, plus F of BC, FC, length of BC, area of BC, E of BC. All of that nonsense equals 0. Okay? So I have one equation, and I have two equations. And I have unknown, 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 unknown. So I have 3 unknowns, and that is not very helpful because I only have 2 equations. So at least I have my compatibility of deformation set up, compatibility. Okay, and I have my equilibrium set up. So let's go back and read what it says about P. The normal stress in the aluminum rod, the normal stress must be limited to 0.62 of the yield. So if I have the yield stress of my aluminum, and the yield stress of my aluminum is 290 times 10 to the 6th, I want to limit that to 0.62. Okay, so let's go back and look at that A to B. So if the allowable stress is equal to the yield stress times 0.62, then I have 290 times 10 to the 6th pascals times 0.62, and I get a yield stress of 179.8 times 10 to the 6th pascals. Okay, so that is my yield stress. Well, how is yield stress related to these internal forces? Well, stress is just P over A. So I have 179.8 times 10 to the 6th pascals equals, what does it equal? It equals this force AB divided by pi over 4 times 0.1 squared. So I can find that my force of AB equals, okay, so I have 179.8 e to the negative, why am I multiplying that to the negative? 179.8 times 10 to the 6th, okay, pi as a number, 4 divided by 0.1 times 0.1 times. So I get this really long number, and we're going to see what number that is. So I'm going to divide by 1,000 to make it kilo, and I have 1412 kilonewtons. That is the limiting stress that I can have inside, okay, inside member AB. That's my limiting stress. If FAB equals 1412, okay, then FA is going to be that negative value. So I can come back here, okay, and if I know that FA, okay, is 1412, and I plug that in here, then I can calculate FC. And when I plug that back in, okay, so do this. When I plug that back in, I get the force in BC, because I find force C. If I know force C, I know force BC. I find the force in BC is 308.974 kilonewtons. Okay, so I've met the requirement of 0.62 yield, and I've calculated now the internal force of BC. And what should I always do? Okay, I have force AB is 1412 kilonewtons. That makes force BC, according to my compatibility equation, of 308.974 kilonewtons. I know that this one is less than yielding because I actually used 0.62. Okay, how does this relate to the yield stress of my material BC, which is brass? This has a yield stress of 124 times 10 to the 6th. Back up. I'm getting carried away here. This is the force. So how do I find the stress in BC? Force of BC divided by area of BC. So I have 308.974 divided by pi over 4 d squared. And if I work this out correctly, I get 157 times 10 to the 6th pascals. This has to be less than the yield stress of my brass. Is it less than? My yield stress for brass is 124 times 10 to the 6th. Okay, so I have limited the P to the yielding of the aluminum on the bottom, but in doing so, I've caused yielding in the top. And there are two ways that I could go about this. Because I already want to limit this, we'll talk about this another time, we could defer some of the force that we found in BC. We could defer it to AB and let AB carry it. Kind of like if we're in a tug-of-war, AB and BC are in a tug-of-war against another team. And if BC kind of like poops out and needs, you know, AB to pick up the slack, AB can do that. It's really cool how materials do that. But because we're already at the limit for AB, we're going to have to reduce that load P that we thought we were going to have. Because we were fine here, but I ended up with yielding at BC. So if my yield stress of BC is 124 times 10 to the 6th, and that equals force BC over area of BC, which is force BC over pi over 4.05 squared, then the maximum force I can have in BC, okay, the maximum force I can have in BC is actually 243 kilonewtons. Okay, so I designed and I based it on the yielding of material AB, and I calculated an internal force of 1412. That put my force in BC at 308. Okay, so I can see that that P was about 1700. But when I checked yielding, my bronze yield, the brass yield. So I have to go back now and I have to use that brass value. My yield stress of the brass is limiting what that force can be. So the most that we can have in the brass is 243 kilonewtons, not the 308 we got when we used the aluminum as the limiting. So now that we know this little value, we have to go back again. Force A length AB, area AB, EAB equals force C, length BC, area BC, EBC, and this is now my limiting. So if I have 243 times 10 to the third newtons for my force, and I know the length and the E and the A, and the length and the E and the A, I can now go back, this all equals 0, I can go back and solve for my force at A. And when I do that, my force of AB is now 1,113 kilonewtons. This value is smaller than the one that I was allowed with 0.62 yielding. But again, going to the design for AB caused BC to yield, and I can't have BC yielding. So I went back and used BC as my yielding material to recalculate, which reduced that force in AB. So now I have a force in AB of 1113 kilonewtons, and I have a force in BC of 243 kilonewtons. This one is right at yield force. This one is less than 0.62 times yielding, so we are good to go. We are no longer yielding. And I can take 1113 plus 243, and I get a value of P of 1356.25 kilonewtons. So that is what I could apply to my system so that I don't have yielding of BC, and I am less than 0.62 yield stress of AB. Okay, and now if I wanted to calculate deltas, well, delta AB is force AB, length AB, area AB, EAB. I have the force and all of this information. And I could do the same thing with BC. When I plug all of these in, I should get that they are equal and opposite. They are the same value. If they are not the same value, then I have messed up my math, and I have just grown used to checking everything.